The global climate is in a state of peril. The Anthropocene epoch has pushed the Earth beyond any stable means. The rate of human consumption is no longer in an equilibrium with the Earth's regeneration of its resources. With over 8 billion people on the planet, humans have been a catalyst for the collapse of the current climate system in our world today. We have triggered the 6th mass global extinction, destabilized our Earth's natural climate feedback system, and altered our planet's landscape in ways unlike ever before. Climate change has always been a reality of the dynamic nature of our planet, and long-term shifts in global temperature and weather patterns will continue to shape our planet until the end of time. But fluctuations in global averages from natural climate cycling is a far cry from the demand that we have placed on Earth from fossil fuel use, anthropogenic industries, and agriculture. We have caused the amount of atmospheric carbon dioxide to increase with such severity that we have disrupted global climate cycles and weather patterns, making them far removed from any natural processes. Climate change is the cumulative response from the Earth's climate feedbacks to external forcings that change the amount of heat energy on the planet. Incoming solar radiation is either absorbed by the Earth or reflected back into the atmosphere by the Earth's albedo. Currently, the Earth is absorbing about 71% of the sunlight that reaches its surface. Positive radiative forcings and positive climate feedbacks have driven the Earth's temperature to increase by approximately 2 degrees Fahrenheit. The increase in temperature has, in return, led to extreme fluctuations in the Earth's weather patterns. And as humans continue to contribute to the increase in greenhouse gases, this temperature increase continues to be amplified by a multitude of other climate feedback mechanisms. Humans have altered over 75% of the Earth's landscape, which has also led to an acceleration of climate change via positive climate feedbacks. As atmospheric temperatures continue to rise, gas emissions create the greenhouse effect, causing heat to be trapped in the Earth's atmosphere and on the Earth's surfaces. Anthropogenically driven concentrations of greenhouse gases have been the catalyst for countless positive feedback loops. Atmospheric carbon dioxide has increased by over 150% since 1750, and as a consequence, the area of sea ice has declined significantly on our planet. At about 19,750 kilometers squared on average from 1979 to 2021, to only 14,000 kilometers squared in 2022. Decreased sea ice area lowers the Earth's albedo and encourages the Earth's energy uptake at its surface to increase. Dark land and water that was once masked by the reflective nature and power of sea ice amplifies the Earth's rate of heat absorption. Positive radiative forcing also causes a strong feedback loop in the climate system as evaporation rates increase, raising atmospheric water vapor levels. Water vapor is also a greenhouse gas, and climate modeling has shown water vapor feedback doubles the rate of global warming. Increased atmospheric water vapor levels also drives extreme weather events. The more water vapor in the atmosphere, the more energy it is holding, which also fuels the storms to intensify, particularly over land. The complex nature of the Earth's climate is nothing new to our planet today. For billions of years, the lithosphere, hydrosphere, biosphere, and atmosphere have all endured immense shifts in climate. Weather and climate variations from decadal to millennial have left no earthly stone unturned. As the Anthropocene brought with it advances in technology, our understanding of the Earth's climate has increased through data collection and mathematical climate modeling. Systematic weather data records became a standard of climate science around the world and in Colorado in the 1870s. And the data gathered, coupled with the use of paleoclimate indicators, has since allowed climatologists to reconstruct the Earth's climate history. Furthermore, it has reinforced that the recent spike in greenhouse gases can be attributed directly to humans. Paleogeology has been used to reconstruct a timeline of the Earth's climate events and history over the course of millions and millions of years. Colorado's paleogeologic reconstruction indicates that 544 to 245 million years ago, Colorado was mostly covered by shallowed inland seas, evident in the thick layers of marine sediment in the state's geologic record. The first mountain building process of the ancestral Rockies occurred about 285 million years ago, and the land was raised by Africa and North America coming together. But those ancestral Rockies eroded with the formation of the Western Interior Seaway. The Western Interior Seaway formed about 100 million years ago, and at about 2,600 feet deep and 600 miles wide, the seaway split North America into two large land masses, which is evident from the extensive downwarping of the continental crust in the geologic record. Carbonate deposits indicate the climate of the time was warm and tropical. The seaway created isolated populations of plants and animals, causing genetically divergent land populations. Eventually, the seaway was displaced by the slow uplift of the continent. And beginning around 75 million years ago, the Rocky Mountains of today began forming in a tumultuous time of volcanism and mud flows. Over the past 700,000 years, there have been at least 6 major glaciation events. Major periods of glaciation are one of the strongest erosional forces on the planet, and that is what is responsible for shaping the Rocky Mountain National Park as it is today. Glacial erosion is an incredibly strong force, as glaciers are massive amounts of ice and snow atop land that are massive enough to carve and crack and push rocks of any size and shape. Major periods of glaciation drop sea levels and alter the Earth's landscape, as well as the composition of the species at the time. Around 12,000 years ago, the latest ice age ended, which can be seen in the geologic record by the striations created from the glacier scraping over the Earth's surface. The end of the last ice age brought about massive and catastrophic flooding in the Colorado region, evident by the transport of massive flood boulders in the geologic record. In the past 100 years, Colorado has seen increases in average temperatures and gradual decreases in precipitation. The two climate factors have led to seasonal shifts and a steep decline in snowpack, which has reduced the volume of the Colorado rivers and streams. Decreased runoff from snowmelt has also limited the state's access to vital water supplies needed for agriculture and livestock. Colorado has had multiple cycles of drought over the last century as well, but as global warming continues to intensify, the anticipation of relief is no longer on the table. Colorado also has a long, intimate history of wildfires, but in the last 100 years, a dramatic change in the intensity of the fires has been greatly concerning. In the 1960s and 70s, fires burned less than 100,000 acres per decade, but by the 2000s, the average decadal acreage consumed by fires in Colorado became more than 200,000 acres per 10 years. Seasonal flooding has also been a long-standing weather event in Colorado history. But like all weather events, the scale of the impact is projected to increase, especially as fires continue to alter the stability and structure of the topsoil here in Colorado. In 2019, Colorado passed a bill with some of the most ambitious greenhouse gas reduction goals in the U.S. The Climate Action Plan is set to reduce greenhouse gas pollution by 50% in 2025 and 90% by 2050, from atmospheric levels measured in 2005. Climate change mitigation strategies are being implemented to protect the state's grasslands from conversion, which keeps the carbon sequestered there from entering the atmosphere. In addition, planting trees to help forests recover more swiftly from fires and erosion and improve air quality is an effort in full swing. Greener forms of transportation aim to reduce greenhouse gas emissions from driving, which is the top contributor in the state to emissions. 28% of the state's carbon emissions come from building operations. Decarbonizing building stock is another initiative that will reduce atmospheric carbon, improve indoor air quality, create longer-lasting infrastructure, and increase climate change resiliency statewide. And those changes cannot come soon enough, as Colorado approaches its 23rd consecutive year of drought climate, sending Colorado spiraling into its driest times yet. As everything continues to become hotter and drier, Colorado is facing some of the most water-scarce times ever in its history. Feeling the heat in full force is the Colorado River and the Colorado River Basin. With the average flow of the Colorado River being reduced by nearly 20% since 2000, low water levels are bringing about unprecedented challenges. As it stands now, even years of good precipitation won't bring back the levels of the Colorado River. In this dire state of drought, the likelihood and intensity of wildfires is hot on our state's heels. And to make matters worse, a major pine beetle outbreak has resulted in extensive lodgepole pine mortality in the forests. Thriving in the high heat and dry weather, the mountain pine beetle has ravaged the Front Range. And as the forests are killed by the massive outbreak, soil erosion is exacerbated, and desiccated trees litter the forest floor with a layer of kindling. Colorado's economy is stabilized by the state's recreational tourism, but the degradation of our forests and the decline of the Colorado River threaten the industry with collapse. Drought and depleted snowpack further threaten our state's agricultural industry and the livelihood of farmers and ranchers. Projections made by climate models indicate that by 2050, the state will see an average temperature increase of 4 degrees Fahrenheit. The plains are projected to shift westward and upslope. Summers are forecasted to warm more than the hottest 10% of summers from 1950 to 1999. Increasing temperatures will lead to less and less snowpack, meaning less runoff each spring. Drier and hotter riparian habitats and fisheries will alter aquatic resources for humans and wildlife. Degrading water quality is of concern, as well as lower moisture content threatens the growing season and wildlife's habitats. Shifting geographic range of species threatens Colorado, with invasive species and the loss of native species as they leave in search of cooler regions. And in spite of the imperfect nature of climate models due to the limitations of computers, it is understood that the level of uncertainty is not significant enough to offset the severity of impending climate change. The ability of climate models to represent complex natural interconnections or replicate extreme events that do not follow a specific pattern only emphasizes the importance of using their most extreme predictions as the baseline for the disturbances we can expect as we move forward. As we move further into the unknown of trails blazed by climate change driven by human-induced increases in greenhouse gases, the anthropogenically influenced calamities faced by the Earth will surely be anything but natural. Understanding the history of our planet has been critical to our conceptual grasp of the climate conditions in the future being at least as severe as any time when our planet has been in an extreme climatic state. And even through making relative comparisons, we still do not have an archive that communicates the changes that may be caused by the atmospheric concentration of greenhouse gases today. What natural processes and climate cycles will be preserved is a global state that won't be fully understood until centuries and maybe even millennia from today. Even mitigating our contribution to climate change to the best of our ability going forward will not immediately slow the trajectory of how much our planet is going to change. A dangerous path lies ahead, and we stand to lose everything we once believed our species to be creating. A global season of suffering is upon us, and that is a climate that we cannot change. In a state of regional and global fragility, we can only prepare for the worst while hoping for the best. Resource allocation and emergency preparedness have reached far beyond critical in their necessity, and tragically we have not come close to the time at which climate begins to stabilize again. Moving forward, the only certainty is that nothing is certain here any longer.